Exploring space is an adventure with unique challenges. In environments that are hostile toward humans, machines must do our exploring for us. These unmanned adventures present unusual problems. This planetary rover requires the automation and integration of many different experts. The system will have to look for samples, build its own habitat, and deal with arising problems without human assistance. But Mars is very far away. The development of a permanently manned space station is a much closer goal which NASA aims to achieve in the next decade. In addition to providing an intermediate base for deeper space probes, the space station will serve as a research laboratory in space. On Earth, such research scientists rely on the support of a town of facilities engineers to keep the equipment and utilities of their lab functioning. Often, many engineers may be needed to support a single piece of complex hardware. Astronomical costs make it impossible to send the entire support crew, and scientists should focus on science. Thus, we must reduce heavy crew requirements on station by mapping the infrastructure of an engineering support town directly into the space station. All of these challenges require that machines become more autonomous. What does it mean to be autonomous? The dictionary describes autonomous as an adjective meaning independent, self-contained, and self-governed. Individual humans and other animals are the most obvious examples of autonomy. Human autonomy is illustrated by our ability to control complex activity in diverse and changing environments. Teams like this astronaut crew illustrate common examples of autonomy at a larger grain size. Autonomous systems can be viewed as a three-component system. First, there is a physical object, nothing more than a functional piece of hardware. The object is connected to an interpretation component, which interprets the world through the object's sensors. A selected interpretation is then passed to the response component, which controls the physical movement of the object throughout the response. Autonomy requires both cognitive and executive behavior. Cognitive behavior focuses on recognition problems, such as identifying what, who, or how many exist in a given situation. Executive behavior focuses on execution problems, such as deciding how, when, and why events occur. As a system incorporates more executive behavior, the issue of real-time deadlines takes on an increased urgency. Real-time means that the system must respond within given time constraints. New technology had to be developed in order to qualitatively model the real-time executive behavior necessary for autonomy. The Systems Autonomy Demonstration Project, SADP, is a joint project between Ames Research Center and Johnson Space Center. SADP was sponsored by the Information Sciences and Human Factors Division of NASA's Office of Aeronautics and Space Technology to demonstrate autonomous system technology. The combined Ames-Johnson Space Center effort has provided technology transfer from the research community to the real-world engineers. The SADP team has developed Texas, the Thermal Expert System. Texas is a real-time, real-world autonomous expert system which monitors the behavior of a sophisticated thermal system. The system autonomously recognizes, isolates, and recovers from faults in the thermal system. This is the actual thermal hardware at Johnson Space Center in Houston. This is a very complex piece of hardware representing a new thermal technology. The new thermal technology involves the use of a two-phase system. This means that the cooling agent, ammonia, exists simultaneously as a vapor and a liquid throughout the system. Here is an overview of the Texas architecture. Texas sits on one Lisp machine. HITEX, the human interface to Texas, sits on another Lisp machine. These two machines communicate to the thermal hardware through a data acquisition and control system. At Johnson Space Center, thermal engineers are testing space station thermal system designs. They monitor sensors and gauges connected to the hardware. Then, when anomalous events occur, they perform fault recognition and recovery procedures. The SADP group has developed tools which allow these engineers to encode their procedural expertise directly into the thermal system. The autonomous thermal system can then function as an extension of the human experts, who cannot actually be sent into space. This was done by developing generic software toolkits. The model toolkit is for building dynamic models of physical objects. This toolkit is an extension of Key, designed for combining quantitative with qualitative causal modeling. Qualitative means that the model is represented using symbolic descriptions, like the words increasing and decreasing. Processing these symbols allows the model to describe abstractions of quantitative data, such as a trend. Additionally, qualitative modeling is usually considered more flexible due to a more abstract point of view. Autonomous systems must actually combine quantitative and qualitative analysis for maximum power and flexibility. Object-oriented 2D graphics provide a flexible interface for model construction and editing. The structure and conceptual components in a physical system are represented with frames. Model objects are represented in hierarchy such that class-level objects define attributes inherited by class member objects. Parameters such as temperature and flow are also represented as classes of objects with value, state, and history information. A truth maintenance system is used for maintaining a logically consistent set of beliefs as the model changes. It is also used to trap conflicts between expected and observed sensor readings. When conflicts are recognized, hypothetical worlds are created in order to consider alternative interpretations of data. A single alternative world will be selected as the most believable and used as the current model. MTK uses interval ranges to represent qualitative descriptions, and parameter ranges to represent quantitative uncertainty in the model. Particular model states will trigger fault diagnosis rules, which provide inference support for fault detection and isolation. These features were used to build the interpretation component in Texas. The Executive Toolkit, XTK, provides tools for organizing activity in distributed autonomous systems by modeling the animated processes in a domain. This executive behavior complements the cognitive behavior of MTK. XTK is a multitasking and procedurally expressive extension of the Key reasoning system. In XTK, qualitative procedures are represented as goal-driven, non-deterministic tasks. Additionally, XTK provides mechanisms for processing subtask success and failure events. XTK allows knowledge engineers to capture domain-specific control knowledge by augmenting traditional deductive expertise with complex conditional and iterative control descriptions. XTK also allows knowledge engineers to capture application-specific control knowledge when integrating activity modules and reasoning paradigms within an expert system. Traditionally, control knowledge is difficult to capture in a structured format. However, control within XTK is organized as a team of communicating experts, using a concise and consistent representation to span the continuum of system activity. XTK provides high-level access to model knowledge, intertask communication, and tracing facilities. These features improved our ability to perform rapid prototyping, maintenance, and testing of the Texas control and response mechanisms. XTK is currently being used to develop control schemes in 2 other NASA applications. These tools are used to model the actual thermal knowledge extracted from domain experts. There are three groups of behavior in Texas: normal operations, system-level fault processing, and component-level fault processing. The normal operations include procedures for system startup, system shutdown, and temperature set point change. The system-level faults include inadequate fluid level, bad motor power draw, bad evaporator flow, inadequate subcooling, unstable system temperature, unstable evaporator temperature, erroneous instrumentation. Component-level faults include slow leak, motor failure, blocked evaporator, control valve failures, controller actuator failures, excess waste gas, excessive evaporator heat load, liquid level sensor failure, pressure sensor failures, loss of heat rejection capability. As an example, we will examine a blocked heat exchanger fault. If trash or a valve failure prevent fluid from reaching the evaporator, it will go dry and overheat. The Texas Data Acquisition System, TDAS, receives raw sensor data from the hardware, calculates trends, and compares values against allowable range limits. TDAS only sends values which violate predetermined limits, instead of flooding Texas with static sensor values at each update. The partial loss of flow due to the blockage has been observed. However, temperature trends are not yet increasing. As Texas receives updates of significant data from TDAS, values are propagated within a symbolic model of the thermal bus. A truth maintenance system is used to keep track of which beliefs are justified by current facts. Inside the model, values and trends are mapped from numbers to symbols, such as very high, nominal, or decreasing. Texas discovers faults by matching these symbols to known fault symptoms or through resolving belief conflicts. While we were away, the evaporator has dried out and temperatures are rising rapidly. An evaporator testing expert has now been created by Texas to test the evaporator. This task is now toggling the valve in order to test the valve and dislodge trash. With the valve reopened, Texas has now restored full flow and the thermal bus returns to normal operation. A major component in an autonomous system is the capacity for hypothetical reasoning. In the interpretation component, Texas uses hypothetical reasoning to choose between alternative interpretations of sensor data. The system actually maintains alternative models in parallel. The interpretations are explicitly compared, and the most believable candidate is selected as the recognized fault mode. A good response component also relies on hypothetical reasoning because a correct response sometimes needs to be planned. Planning involves analyzing the effects of simulated response alternatives. Currently, responses are pre-planned on ground, then canned into fault detection, isolation, and recovery, FDIR books. These books are referenced by astronauts or by human engineers on the ground, who then pass the information to the astronaut. By connecting an integrated interpretation and response component directly to the hardware itself, new classes of difficult real-time situations can be qualitatively modeled. There is more to a response than planning the appropriate procedure. The procedure must actually be executed in order to change the situation. This involves actual manipulation of the hardware, thus completing the cycle. Texas combines human and machine execution. The machine does the execution in the cases where the software can toggle valves or exploit redundant paths in the system. However, if a critical component must be replaced, the human must step in. HITEX is the human interface to Texas. HITEX provides color-coded sensor displays, schematic diagrams, and graphic plots to present only the highest interest information about the behavior of the thermal hardware. HITEX also uses graphic and text displays for dynamic, interactive explanation of Texas behavior. Through high-techs, the operator can interact with the user about warnings, alarms, and action confirmations. The operator has the ability to approve or modify actions that Texas is performing, or to change the scope of the machine's responsibilities.
The Texas interface is an improvement because it displays all the information from our previous systems on one screen in a condensed fashion. Plus, it presents new information by detecting faults and suggesting their recovery procedures. This combined capability should make thermal operators more productive.
The thermal crew's acceptance of automation is important feedback about automation technology coming out of the research laboratory. In summary, we learned of the SADP's Texas project, which demonstrates autonomy for the thermal system on the space station. The system communicates at a high level with humans and requires minimal assistance by space station crew. The SADP group has made significant progress in the development of this enabling technology called autonomy. The lessons learned and technology developed here have brought us closer toward preparation for the most challenging adventures we will face in space.